Hello everyone. So for the last few days uh, we are doing this module, that is the DC network theorem. So today also we are going to discuss over this module on the topic maximum power transfer theorem. So already we have covered different topics like KVL, KCL, superposition theorem, Thevenin theorem, Norton's theorem. So already we have gathered so what is the concept of different solving different circuit. So today we are going to understand so what is maximum power transfer theorem. So before starting the theorem, so I have to say you that this transfer theorem is not some such different theorem from other theorem, other Thevenin's theorem. So it is an application of Thevenin's theorem. So as I am telling that it is an application of Thevenin's theorem, so to do this theorem, maximum power transfer theorem, so we have to first understand so what is Thevenin's theorem. So before starting so of this maximum power transfer theorem, I want to tell you what was Thevenin's theorem. Already that thing already we have done already though. So just 1 to 2 minutes I will take, and within that I will going to tell you what is the Thevenin's theorem. So say coming to the diagram, say this is our circuit, and already we have taken the same example when we have done the Thevenin's theorem over there. So there we have seen that so if we have a circuit like this, Vs is the supply voltage, R1 small r1 r2 and r3 are the circuit resistance, and RL is the load resistance. Now we want to find out what is the current passing through this load resistance. So what we have done over there, so as per the Thevenin's theorem, so first we have removed the load resistance, then what we have done, so then we have made that terminal open and we have find it out the open terminal voltage. So that voltage we have given a name Thevenin's voltage, VTH. I think you can remember this one. So that was our first step. In step 2 what we have done, so in step 2 we have made the circuit independent of source, any kind of source, maybe voltage, maybe current, and after that we have viewed the circuit from the open terminal. So where is the open terminal? From where we have disconnected the load resistance. So from there um, we have discounted load resistance, and from there we have to find out the equivalent resistance of the circuit. So we have already done this, and after that at the end what we have done, step 3, that the first step we have find it out the equivalent voltage source, that is VTH. In the second step we have find it out the equivalent resistance, that is the RTH, and initially in the solving procedure we have disconnected from the circuit the load resistance. Okay, so we have to connect all these three components in series, and we have to find out the series current, that will be our load current. So that is just I am remembering you that things already we have done before. So that concept, that same concept, the same procedure we have to apply over here. But then why there is a different name from to this particular theorem, maximum power transfer theorem? So the name behind this theorem is that its concept. What is the concept? The concept lies in the name itself, maximum power transfer theorem. So here we are going to find out, so when through some load resistance maximum power can be delivered. So when, so if I ask you when it can be delivered, so you can say that we know that power formula is equal to B into I. So when voltage and current will be increased, power will be increased, but for a particular circuit voltage is fixed. So we can say that if we can increase the current, so we can increase the power. So when we can increase the current, we can decrease the resistance value. So up to which value we can decrease the resistance value? Can it can be zero? No. In real life the load resistance cannot be zero. So what should be the value? 1. ohm, 2 ohm, 3 ohm. Is there is any specific value? No, there is no specific value. It depends upon the circuit. So now we are going to see what should be the value of load resistance for which through the load resistance maximum power can be delivered. Okay, so this is the theorem. That means through any circuit, through any load resistance, what is the maximum amount of power can be delivered. So this is the main idea of the theorem. So first coming to the statement, so as you can see over there, a resistive load being connected to a DC network receives maximum power. So it is told that there is a resistive load, it is connected to DC network. So for your better understanding, it can be applied to the AC circuit also. Okay, so for your simplicity, for your as per your syllabus, we are discussing here only with the DC network, DC source. So again, a resistive load being connected to a DC network receives maximum power when the load resistance is equal to the internal resistance known as the Thevenin's equivalent resistance of the source network as seen from the load terminal. The maximum power transfer theorem is used to find out the load resistance for which there would be the maximum amount of power transfer from the source to the load. Correct? So it is told that what is told over here, that when the load resistance is, see, just check this portion, when load resistance is equal to the internal resistance known as the Thevenin's equivalent resistance. So in the Thevenin's, when we have done the Thevenin's theorem, so there we have to find it out in step 2. We have find it out the equivalent resistance of the circuit. Okay, so when we have find it out the equivalent resistance of the circuit, so at that time what we have done, already I have told 2 minutes before, that we have to remove all the kind of sources. That means we have to make the circuit independent of source, and we have to view from the load terminal. That means from where we have disconnected the load and find out the what is the equivalent resistance of the circuit. So that equivalent resistance, if that equivalent resistance is equal to the RL, that means the load resistance, then only the maximum power can be delivered through the load resistance. Why? Because because the circuit resistance is already present over there in the circuit. So whatever is the mm, load resistance value, so due to the presence of the circuit resistance, there must be some drop. So we can say that the amount of the load resistance must be equal to the circuit resistance, internal resistance. Then only we can transfer the maximum power from source to the load. Correct? So this is the definition. Now coming to the use. What is the use? The theorem is used to find out the value of load resistance for which maximum power can be transferred through load resistance. So already we have discussed that one. Okay, now point number 2. So as I have told that this theorem can be applied to the AC circuit also, so that thing is written over here. So the maximum power transfer theorem is applied to both DC and AC circuit. Okay, the only difference is that in AC circuit the resistance is substituted by impedance. Okay, so already this concept we know that with a DC source, inductor, capacitor cannot work. Inductor act as a short circuit, capacitor act as a open circuit, so we cannot consider inductance and capacitance when we are working with a DC source. But when we are working with the AC source, we can consider. Now, if a circuit has R, L, and C, so combining those three components, we have an impedance concept. So at that time, when we're discussing about AC circuit with the AC source, then we have to take the impedance value. Okay. Now the application where we can use this one, the maximum power transfer theorem finds that application in communication systems which receives low strength signals. So say we have a signaling system, correct? So low signaling system, so when there is a circuit, the circuit has some resistance value, Now at some point we have to receive some signal. So when it will receive some signal, so there is a variable resistance. So when the resistance value is changing, and when the resistance value of that particular circuit is equal to the signaling circuit resistance value, at that time there will be a signal transfer. Okay, and it is also used in the speaker for transferring the maximum power from an amplifier to the speaker. So same concept, by changing the resistance value we can change the amount of power transfer. So how much we can change the resistance value? Up to the internal resistance of the circuit. So when the internal resistance of the circuit is equal to the load resistance value, then only we can transfer maximum power. So this is the main point over here. Okay, so now again, in each theorem I have discussed with you this concept, that what is the concept? The concept is that the linear element, bilateral element, what are those? What are those concepts? So those concepts are that this maximum power transfer theorem, Thevenin's theorem, Norton's theorem, superposition theorem, all theorems can be applied in the circuits which contains linear elements and which contains bilateral element. So what is linear element? Linear element means an element through which the VI characteristics is linear. So what is the linear property or the linear characteristics? Linear property or linear characteristics is such that where the V and I uh, property is linear, that means which follows the straight line equation y is equal to mx plus c. So that means in easy way, if I want to tell you, if we have to visualize what is linear property, then we can say that when we are increasing the voltage value, the current is increasing, and when the voltage value is decreasing, current is also decreasing. That means V and I. So if we take a graph of that one, and in the x-axis if we consider voltage, and in the y-axis if we consider the I, that means the current, and if we increase the voltage value from 0 to up to some extent value, and current value from 0 to some extent, so you can say that when voltage is increasing, current is increasing, when voltage is increasing, like that way. So we will get a straight line equation. So that is the linear property. So linear property includes in the resistor. Okay, so here I have given the same example. So like this way, bilateral property. So what is bilateral property? So bi means both. So I am repeatedly for each theorem I am discussing those things, because these are very important fundamental concept you have to remember. So what is bilateral? Bi means both, as I have told you, that both direction current can flow. Okay, so this is the basic idea. That means, say we have a resistor symbol like this way. So if we so this resistor, we have two terminals, left and right. So if we connect a source in the left hand side, so current will flow from left to right, and if we connect a source in the right hand side, the current will flow from right to left, provided the terminal connected to the resistor, so that should be higher potential, then only whatever I have told, that is possible. So my point is that through this resistors, particular this resistor I am discussing, that the current can flow from right to left or left to right, correct? So if it is possible, then this material, this element is known as the bilateral element, and the circuit which contains this bilateral element is known as the bilateral circuit. And this maximum power transfer theorem, that is actually the application of Thevenin's theorem, can be applied in such circuits. Okay, linear, bilateral. Okay, and the components must be passive. So passive means which doesn't has any kind of source of EMF. So there we can use this theorem. Okay, so now explanation. So that is the main part. So we have discussed the statement where we can use what is the terms to know, that means the linear, bilateral concepts that we have discussed. Now we are going to discuss. So in the statement it is told that when the internal resistance is equal to the load resistance, at that time maximum power can be delivered. But from where we have got the concept? So there should be some logical view, some logical derivation, some mathematical derivation should be there. So now we are going to do that. So from where we have got this concept that when this RL is equal to RTH, at that time maximum power will be delivered. So for that, see here two figures are there. Figure 1, so it is shown that there is a DC source, okay, and DC source is coming to the resistance, correct, very simple. So here also in this next diagram also same thing is there with the elaboration version, that this DC source has its own some resistance value, so shown in the dotted line. So this is the VTH DC source and its internal resistance is this one, correct. So say for simplicity this is the RTH, the Thevenin's resistance, the internal resistance of the circuit, and it is this whole system is connected to the load resistance, and it is shown that this load resistance is a variable one. So now if we change the resistance value, then at a certain point will appear when this RL value will be equal to this RTH. So at that time we can find out that at that time the power that is transferring to this RL will be maximum, correct. So this is the condition. So when we have done the Thevenins, so there we have seen that the last step we have done this, the VTH, RTH and RL all are connected in series, and we can find out some very simple series current. So if we consider this is the VTH, this is the RTH and this is RL, so the current passing through this loop will be this I is equal to voltage by total resistance RTH plus RL. So that is done over here, VTH by RTH plus RL, correct. Now see what this derivation is very important for understanding and for semester also, okay. So very carefully listen what I am telling you, the very easy to understand, so just you have to listen carefully. So first we have written this current equation, that is I is equal to VTH by RTH plus RL. Then we know that while the power delivered to the resistance load is given by the equation, that means when some power is delivering through the load, so at that time the load power equation is given by PL is equal to IL square into RL. So here the same equation is given, PL is equal to I square into RL. So now this I is given by the expression of VTH by RTH plus RL. So if we put that over here, so what we'll get? See this one. PL is equal to, in the bracket, first bracket, VTH by RTH plus RL whole square into RL. So it's the same expression. Just we have put it the expression of this I VTH by RTH plus RL, correct? Now we know that, so when now our point is when this PL value, the load through the power through the load, when this value is maximum. So this value is maximum when we know that from concept of mathematics, when its first order derivative is equal to 0. So now we are going to do that. So it is overwritten also over the PL can be maximum by varying RL, and hence maximum power can be delivered when dPL by dRL is equal to 0. So now we will going to do that and we will find out what is the result. So we have done that. So in the upper section what we have, VTH square into RL, and below section what we have, RTH plus RL the whole square. So now that means the derivation we are going to do in concept of mathematics, that is A by B, derivation of d dt of A by B, like that. So if we do that, so what we can find out, dPL by dRL is equal to, so first we know that B square, so here what is the B, RTH plus RL whole square. So RTH plus RL whole square, its whole square again, so that means 2 plus 2 to the power RTH plus RL 2 to the power 4. So actually in the next line we are getting this one, and in the upper section see B into ddt of A minus A into ddt of B. So that we know from the concept of mathematics. So here we have done that. So This B means the denominator, so RTH plus RL whole square, it is remaining same, and DRL of VTH square, VTH square into RL minus VTH square into RL into DDRL in, into RTH plus RL the whole square. Correct? Now next line, what we have done, it is now to the power 4, and here if we make the derivation, first order derivation of this whole component, so here you can say that this Vt squared is the constant, so it will coming out, and the derivation of RL with respect to DRL will give us a 1. So see, as we can see over here, there is a 1 actually, so it will remain same, RTH plus RL whole square into VTH square minus this will remain constant VTH square into RL into, so see here this is the whole component, so as we know when we make the derivation, so power will be here, so this power 2 will be here, and if we make the derivation, so there is a power minus 1, so 2 minus 1, that is 2 to the power 1 here, and again the inside that we have a RL, so derivation of DRL into RL, that will give us 1, so there is a 1. Okay, so just now we are doing the simplification, we have taken the VTH square common, and inside that what we have, RTH plus RL minus 2RL by RTH plus RL cube, so 1 RTH plus RL is cancelling out from there. Now again we are simplifying this one, so there is a minus 2 RL, there is a plus RL, so the result will be minus RL, so RTH minus RL. So this is the simplification. um, so from the concept of mathematics, we know that when the first order derivative of a function is equal to 0, it has a maximum value. So we can say that this whole component is, if it is equal to 0, then it has a maximum value. So that's why we have written that the component written over here, that is written over here, so Vt square into Rth minus Rl by Rth plus Rl whole square is equal to 0. So now if we take the square term over this right hand side, so it will be 0, and now if we simplify, so then we can say that, say RTH minus RL is equal to 0, so RTH is equal to RL. So after that derivation we can say that, see, when the Thevenin's resistance, that is the internal resistance of the circuit, is equal to the load resistance, there we can find out the maximum power transfer through the load resistance. Okay, so like this way, we can find out what is the value of load resistance for which the maximum power can be delivered. Now we know that RT is equal to RL is the condition when the maximum power will be delivered. Now in the power equation, if we put this value, okay, so what was the equation? Our equation is P max equation, that is VTH square into RTH by RTH plus RL square there was, but as RTH is equal to RL, so we have replaced RL with RTH, so here we have put the RTH, so 4 RTH square, so 1 RTH from upper and lower section will cancel out, so the ultimate result is the VTH square by 4 RTH. So this is the amount of maximum power that can be delivered through the load resistance when the load resistance value is equal to the Thevenin's resistance of the circuit. Okay, so this is a simplification we have done. Okay, so this is all about the maximum power transfer theorem. Thank you.